Howdy. We're going to talk today about finding limits at infinity using analytic techniques. Specifically, we're going to be talking about finding the limit as x goes to infinity of f of x, finding the limit as x goes to negative infinity of x. We're going to focus most of our attention on rational functions because much of our effort is going to be dedicated to graphing these rational functions. But we're also going to consider exponential functions a little bit at the end. So I want to begin with something that you learned last year, which is a look at the limit as x goes to infinity of x to the n, and a limit as x goes to negative infinity of x to the n, where n is a positive integer. We call these functions monomial functions. And you remember from last year, from trig pre-calc, that their graphs look something like this. For n even, the graph looks like a parabola. And the larger that n is, the flatter bottomed and steeper this parabola will be. For n odd, the graph has a characteristic shape like this. And again, the larger n is, the flatter it is at the origin, and the steeper it is. And so from these two graphs, we can actually read out values of limits at infinity and at negative infinity. Because as x goes to infinity, for both the even and the odd cases, these monomials escape out to positive infinity. So that no matter whether n is even or odd, we always get the same value for the limit as x goes to infinity of x to the n. And you want to intuit this by imagining plugging in very large numbers for x, raising them to some positive integer power n, and of course when you do, you're going to get very, very large numbers. Over here, as x goes out to negative infinity, we have different behavior for even and odd. When n is even, as in the case of the top graph, then the limit as x goes to negative infinity of x to the n will be positive infinity again. And here we want to visualize this as taking very large negative numbers and raising them to an even power, which means multiplying them by themselves an even number of times. I'm going to get very large positive numbers as a result. But if I take the limit as x goes to negative infinity of x to the n when n is odd, as in this graph right here, then I get negative infinity. And again, I'm taking large negative numbers and raising them to an odd power. So, the upshot of this is that when I'm taking limits at negative infinity, I have to pay attention to the evenness and oddness of my power x to the n. As an example, we want to consider the limit as x goes to positive infinity of 3x squared. And so we can use a little bit of constant multiple rule or product rule to rewrite the limit, like so. And now we observe that the limit as x goes to infinity of x to any integer power is going to give me infinity. Well, what about the 3? My form for my limit is 3 times infinity. And for this form, we want to visualize taking very, very large numbers and then multiplying them by 3. And when we do, we get even larger numbers. So it is clear that as x goes to infinity, 3 times x squared is going to go to positive infinity also. On the other hand, if I take the limit as x goes to negative infinity, let's say negative 6x squared, then I can again use constant multiple to bring bring the negative 6 to the outside. And now because my power is an even power, the form of my limit is going to be negative 6 times infinity. What does this mean? This means I'm going to be getting very, very large numbers and multiplying them by negative 6 so that I get very, very large negative numbers. In other words, my limit here is going to be about negative infinity because the negative coefficient changes the sign of the infinity. So this is how it works for monomials. If we consider the opposite question, what is the limit as x goes to infinity of 1 over x to the n, or the limit as x goes to negative infinity of 1 over x to the n? Things get very much simpler. Because the graph of 1 over x to the n when it is even goes to 0 in both positive infinity and negative infinity directions. And the graph of 1 over x to the n when n is odd goes to 0 in both the positive infinity and negative infinity directions. So that means whether n is even or odd, whether x is going positive or negative infinity, this will always give me 0. And that's nice. So to recap what we have so far, the limit as x goes to either positive or negative infinity of 1 over x to the n is 0. The limit as x goes to positive infinity of x to the n is always positive infinity. And the limit as x goes to negative infinity of x to the n will depend upon the even or odd parity of the exponent. Now, to put all of this together to finding limits of rational functions, we need just one more piece of information. We need to talk about end models. It turns out that if you have a general polynomial, f of x equals an x to the n plus an minus 1 x to the n minus 1, etc. We've seen these polynomials before. That for very, very large positive or negative numbers, f of x is going to be basically no more than its largest degree term. For very, very large x, I can ignore all of these terms out here. Now, why is that? Let me argue numerically, and then I'll show you on a graph. Numerically, I can ignore these terms because for large values of x, they are going to be overwhelmed or swamped by the large term a. They are small compared to x to the n. Now, just to give you an example so you can understand what I mean, let's make this concrete. Let's say f of x is equal to x squared minus 3x plus 2. Okay? So here's my f of x. And now I want to consider a large number. Now, in the world of math, a large number is a number with, say, 300 digits. But we're going to take what we would consider a medium-sized number in math, and that's a million. And if I take f of 1 million, then what I get is 1 million squared minus 3 times a million plus 2. And if you consider now what this looks like when you multiply it all out, this is going to be 1 followed by 12 zeros when I square that million. Minus 3 followed by 6 zeros and plus 2. And what I want you to observe is that when I add these two terms are so small compared to the largest term here that they make practically no difference whatsoever. And that was just for a medium-sized number like a million. If I try a billion or a trillion, then the insignificance of these terms becomes even greater. And when I get into the truly large numbers, the ones with 200 and 300 digits, then all of these terms, except for the highest powered term, simply drop out. Just to illustrate this with a graph, I want to consider two functions that I have here. I've got f of x equals 3x squared minus 4x plus 5, and I have f of x, we can call that g of x, equals 3x squared. So this is a polynomial, and this is just the highest powered term of that polynomial. And first I have the graph of those two in the standard window size, negative 10 to 10. And when I graph those two functions, here's my f of x right here, and here's my g of x right here. You can see that they're different. So that's in the standard window size. But now if I zoom out so that I look at very large x's, for example, I might look at x's between negative 1,000 and positive 1,000. And keep in mind that for a mathematician, that's a medium-sized number. And we need to make our y values larger too, so you can see what's going on here. When I graph these now, look at what happens. F of x goes there, g of x goes there, and you can't tell the difference between the two graphs. The two graphs are very, very close together. In fact, it's kind of hard to tell the difference between in the x-axis and the y-axis. So the point is that for large x's, f and g are essentially the same. So we call the highest powered term the end model for f of x. And what that means is that out at the ends, for very large, as x goes to infinity, and for very large negative numbers, as x goes to negative infinity, f of x and its end model are basically the same thing. Now here's how we put all this together. Let's say I have a rational function. F of x is equal to 3x squared plus 2x minus 6 over 6x squared plus 9. And I wish to determine the limit as x goes to infinity of f of x because I want to find its horizontal asymptotes. And you remember that the horizontal asymptotes are found through the limits at infinity. So I set up these two limits right here. And now, using the idea of end models, I can say that as x goes to infinity, f of x, the numerator here, f of x, can be replaced with its end model. And the denominator here, g of x, can be replaced with its end model, just like so. And having replaced with the end models, we've got end model replacement. Having replaced with the end models, now some very easy simplification takes place, so that I get the limit as x goes to infinity of a constant, 3 over 6, which is the same as 1/2. And the same kind of thing happens down here. We're going to take the limit now as x goes to negative infinity of 3x squared over 6x squared, which is the same as, again, 1/2. So that the use of end models greatly simplifies your computations, and once you've done like 2 or 3 of these, you can basically do them in your head. Let's look at a couple more examples, and then I'll talk very briefly about exponentials. Let's consider g of x equals, how about negative 3x squared minus 2x all over x plus 1. And we want now the limit as x goes to negative infinity of g of x. So we're going to accomplish this, first of all, with end model replacement. We're going to replace the numerator with its end model, which is negative 3x squared, powered term. And I'm going to replace the denominator with x, its end model. So there's my end model replacement. And now I can do a little bit of simplification. And what I do, I've reduced my rational function, the limit of my rational function, to the limit of a monomial term. And this gives me now, in form, -3 times odd power of x, negative infinity. Which is going to give me positive infinity as the limit. So one more. Let's let h of x be equal to 4x to the 4th plus x to the 5th to the minus 1,000 x cubed all over 1 plus x to the 6th. And what we would like to do is to find the limit as x goes to infinity of h of x. I want you to observe a couple of things about this. And the first thing I want you to observe is that all of the terms except for the highest powered term are really distractors here, because we are going to first pull off an end model replacement. And the end model for my numerator is simply x to the 5th. The fact that I have a really large coefficient over here for x cubed does not matter. It makes no difference. Now in the denominator, we pull off an end model substitution as well. And now we can do a little bit of simplification. Cancel 5 powers of x, giving us 1 over x as our simplified quotient. And now as x goes to infinity, 1 over x goes to 0, and we have our limit. So this is all very nice. Sometimes, occasionally, we will encounter exponentials as x goes to infinity. And I just want to appeal to the graph here, because my rational functions are always going to end up giving me the same limit from left and right, unless that limit is going out to infinity. So you can sometimes get positive infinity on one side, negative infinity on the other. But if I get a numeric value, I'm always going to get the same numeric value from left and right. When you look at the exponentials, they exhibit very different behavior, left and right. The limit as x goes to positive infinity of e to the x is positive infinity. But the limit as x goes to negative infinity of e to the x is going to be 0. And that reflects the fact that out here, as x goes out to negative infinity, the graph of e to the x gets arbitrarily close to 0. The same kind of thing is true, but in reverse, for f of x, or g of x equals e to the negative x. In this case, taking a look at the graph, the limit as x goes to infinity of e to the negative x will be 0. And the limit as x goes to negative infinity of e to the negative x will be positive infinity. Well, I hope this has been helpful and informative to you.